If I drop this glass plate, it's going to fall and break. But what if I told you it wasn't the plate accelerating towards the ground, but rather the ground accelerating towards the plate? Let me explain. Gravity is not a force. Nothing is pulling this ball to the ground. In this demonstration, this fabric is space-time, and this ball is the Earth. Earth distorts the space-time fabric, causing any less massive objects to fall towards it. And if I give it some speed, it appears to orbit. Matter tells the space-time how to curve, space-time tells the matter how to move. But there's a problem. This demonstration relies on Earth's gravity to explain gravity. In space, the ball wouldn't actually roll because there would be no external force acting on it, even if the fabric was curved. Plus, it's a two-dimensional model, while real mass distorts 4 dimensions, including time. Everything moves in a straight line through space-time. Take the moon, for example. We see it orbiting the Earth in a circle, but in reality, it's traveling in a straight line. Mass of the Earth curves space-time, and because the moon travels on space-time, it makes straight line motion appear circular. One way to visualize this is to imagine 2 pairs of people walking in straight parallel lines. On flat ground, they would remain the same distance apart forever. However, on a spherical surface like Earth, the 2 walkers would gradually gravitate towards each other, even if they thought they were walking straight, because the ground beneath them that they have to travel on curves. That's exactly how gravity works. This isn't just with mass, this is with anything that moves through space, including light. During a solar eclipse in 1919, stars near the sun visually appeared shifted from their normal positions. It appeared that the sun's gravity had bent the light around the sun and into our eyes. But light can only travel on a straight line. The sun's gravity just bent the space that the light travels on. To understand all this deeper, we need to look at something called the equivalence principle. Contrary to what we typically think, the act of falling is the exact same act as just floating in space. Imagine you are in a big steel box falling to Earth. Now imagine yourself in that same steel box floating in space. In both scenarios, you and everything else in the box would feel completely weightless. And that is because you both are weightless. They are not similar situations, they are the exact same situation. Now flip the scenario. You're in the box on Earth's surface and you can feel your weight. If you drop a ball, it falls to the ground. Now imagine you're in a box in space, but this time with boosters accelerating you at 9.8 meters per second squared, which is the exact same as Earth's gravitational acceleration. If you dropped a ball, it would fall to the ground just like it does on Earth. It's not because the ball falls to the bottom of the box, it's because the box accelerates into the ball. This is the exact same thing on Earth. If I stood on a scale, in both situations, it would read the same weight. So if the Earth is accelerating in all directions, then why isn't it expanding? We often forget that you aren't just moving through space. If you're stationary floating in space, you're just moving through time. And the mass of something doesn't just curve space like we talked about earlier, it also curves time. And that curvature in time is what allows gravity to happen, and it also allows the Earth to accelerate in all directions without expanding. Let me show you how. This is a ball floating in space near no large objects of mass. I've drawn it like a graph. You can see that the ball isn't moving through space at all, it's just floating. However, as it's floating, it's moving through time. And not just time, this is proper time. This is time relative to the ball. This is the same ball, but this time it's floating near the Earth. You can see that the ball is just moving through time in both scenarios. Neither of them are actually moving through space. But in this scenario that has the Earth, it appears as though while the ball is just moving through time, the ground accelerates and intercepts the ball. We can also see that time is curved in this demonstration. And this is what's happening while a ball is on Earth. And you're thinking, well, Lincoln, I don't see the ground accelerate towards the ball. That doesn't happen. And you're right, from our frame of reference, this doesn't appear to be happening because we don't view the world like this. We are actually in this curved space-time because we are on the Earth. Watch what happens when I curve this paper into the shape of a cone. You can see the ball is only moving through time, but it appears to be falling to the ground, even though in reality, the ground is accelerating upward, and the apple is only moving through time. But from our spatial and temporal frame of reference, the ground doesn't appear to be accelerating at all. The ground just makes a circle, and the ball falls to the ground.